So sampling proportions, we're going to start shifting gears a little bit. And so the idea here, we're going to be able to describe how sample proportions relate to population proportions. So we'll start here. Here's this polling company, and they surveyed 400 likely voters during the primaries. 49% of those people said that they were in favor of Obama, 42% Clinton, 9% undecided. Once the primaries were over, it was found out that the true percent of voters that voted for Obama was 56%. So what we want to look at is how good was this poll? And really to answer this question and be interesting to see, well, how likely is it for the polling company? So really, what's the probability that they found this he had of 49%, something like that, or even more extreme, when in fact the true percentage was 0.56. So we've been talking about this already, but just as a reminder again, p hat is used to describe a sample, and p is used to describe population. So here, right, the polling company did a sample and found that 49%. So what we did with this the first time is we did a simulation, right? We took 100 random digits. 1 through 56 meant they voted for Obama. 57 through 100 were not for Obama. And then we did 400 random numbers. So we generated a list. We put them in, we organized them. We found our p hats. And what we ended up doing as a class, if you recall, was we started kind of putting our proportions up along the board. You guys would stack them up as you guys found stuff. And what we found, these things started to take on a normal shape. Started to center around the true value, right? If those numbers were there, these numbers started to kind of center around 0.56 to 0.58, if you will, right? We kept going through here. And what we saw in class, if you can remember way back when, was we really never got anything as low as 0.49. So the probability within our simulation that we got a p hat is less than or equal to 0.49. I think in all the classes there might have been 1, but it was essentially 0. So it wasn't very likely through simulation. The problem for us, though, is that these simulations, they take forever, especially if you have to do them all by yourself. We had the whole class. So we want to learn a method to make it even quicker. One of the things to note when we did the p hats, when we did all the averages before, these sampling distributions always became normal. Right? They always became normal because of the central limit theorem. Become normal because of what's called the central limit theorem. What that tells us is that when we take big enough samples, these things will start to center around what the true value was, right? And for us, the true value, the p, was 0.56. So if we do a bunch of p hats over and over again, they'll center around 0.56. So again, if we're going to answer this question, if we don't want to find out how likely it is, right, what's the probability that these p hats, 49% of people or fewer, voted for Obama? So again, a chance here to remind you, why am I doing less than or equal to? We always want to find the probability of a given outcome or an observed outcome or something more extreme. That means, if you think about it for just a minute, we were supposed to get 56%. Well, 49 is below it. So 49 or more extreme would be everything at 49 and below. So for us, we're going to take advantage of the fact these sampling distributions, which are always normal, whether we're using X bars or p hats like we've done in class. And what those things are, if we were to take all these different samples, but they're all of the same size, right? Every time we've done it, we've graphed the same size samples each time we've done it from the same population, right? When we did the fishing tournament, the basketball teams, we all used the same data and we all found samples of the same size. And what it's going to end up being if the mean, another way to think about mean, if the center of a statistics sampling distribution, aka if the center of all those p-hats, the center of all those x-bars, is equal to the true value of the parameter, it's called unbiased. So for us, that's pretty much always going to be the case. Because of the central limit theorem, this unbiased thing is always going to happen. These things are always going to center at the true value. So for p-hat, at the point of this particular video, p-hat is an unbiased estimator of p. We just saw it with our Obama simulation. And why is it normal? Well, that's because of the central limit theorem. What we need to realize, right? What this means. So the sampling distribution, so the p-hats are going to be normally distributed. Remember the shorthand here. This is the mean, and this is how spread out things are. Another name for mean, right? This is the center. So the p-hats will center around the true p, and then to figure out how spread out things are, that's the formula we're going to use. PQ over N. Notice we're using the p's over here, right? Everything's p, not p-hat. So certain things must be true for this to occur. So one, we have to have data from a random sample. Two, we want independence of observations. Well, the way that we're going to check that is make sure the population is much bigger than the sample. The question is how big, and really we want to make sure the population is bigger than 10 times your sample. What that does is assure that the sample is not too big, that we're not talking to too many people within the population, because if you start talking to too many people, they can start to affect each other, which affects this idea of independence up here. So there's your second condition to check. And then third, these P's end up being binomial, right? Think back about the Obama thing. They either voted for Obama or they didn't. There's a set number of trials at 400. There's a set probability, and each person was independent. So if we go back and remember what we talked about last unit, when does a binomial become normal? That's when NP and NQ are both greater than or equal to 10. So what you see in those boxes right there, so SRS, we want to make sure that our population is greater than 10 times the sample. NP and NQ are both greater than or equal to 10. So now let's answer the question. What is the probability that p-hat was less than or equal to 0.49? And then decide, well, are we going to trust another poll from this company? So here's the process, right? I'm trying to find the probability that p-hat less than or equal to 0.49. Well, one, I don't want to do all the simulations, so if the three conditions are met, then we're good. Simple random sample. I'm sure it's fine. We need more than 4,000 voters. That's a safe assumption that in the U.S. there were more than 4,000 people voting. And then we need N times P, so there's N, and N times Q to be greater than or equal to 10. So real quick, what I like to do as well is just jot down, so I know the p-hat I'm dealing with is 0.49. The p, the true proportion, was 0.56. So p is 0.56, q is 0.44. Those are both greater than or equal to 10. Because those three conditions are met, it means that the central limit theorem is in play, which more importantly for us means normal CDF is in play. Which means now I can go and start to set up this normal curve to answer the question. So I think about, well, what is the center of all these p-hats? The center of all these p-hats is the true proportion of 0.56. Standard deviation of all these p-hats, we saw was p times q over n. Now, what makes this different than what we've done so far is we were taking a sample of 400 people. We never took big samples before, right? Whereas binomial is always, quick reminder, what's the probability exactly, 5 out of 10. Well, now we're saying, what's the probability a sample, right? So that was the last unit. Now we're saying, probability a sample, you fill in the blank. Right? So that's what's shifting. We have a slightly different formula. So again, this curve is going to center at 0.56. And if we do the math, that standard deviation is 0.025. So it would be 0.585, 0.61, 0.51, 0.535, and then 0.485. Probability statement tells us I'm going to start at 0.49, then shade down. So just based on this curve, it's not going to be much in terms of a probability. For us, we'd like to jot down the normal CDF. You don't have to do this, but if you'd like to, I think it's not a bad practice just to kind of show that we know what goes where. So we got lower bound, upper bound, mean, and standard deviation of this situation. And what we end up finding is the probability. So now we'll go back up and we'll fill this in. That normal CDF gives us a probability of 0.0026, so it's not very likely, right? The probability of obtaining 49% or fewer when we should have gotten 56% is 0.0026. So the company, or so the poll, doesn't appear to be reliable. Okay. And so those are the pieces that we're looking for, right? We want to check conditions. We want to show our work for our mean and our standard deviation, label things appropriately. To me, I think it's worth it. Although you won't be graded on this, or it's not really something that's typically checked, I usually like to write down the difference between p hat and p. That way I know what to plug into my formulas. Let's show this normal curve so we can make sure that we're thinking about the right lower bounds and upper bounds, and we've already got an idea just based on our shading that is not very likely. Feel free to throw down that normal CDF. Just again, typically calculator talk isn't something the graders are going to go straight to looking for. They're going to look for all those other pieces first, but that's just one more piece of evidence we can show them. And then finally come back and let's make sure we write our answer in full context.